Hi, my name is Rickard, and welcome to This Week in My Programming World. So I recently watched a low-level JavaScript video in which Francis implemented a QOI encoder in TypeScript. QOI stands for the Quite OK Image Format, and it describes how pixel data is encoded and decoded into bytes. The whole specification of the format fits on a single PDF page, and the simplicity of the format caught my interest. I got inspired to try and implement a QOI decoder in RLMeta. So RLMeta is this programming language I've been working on, in which you can write parsers and tree transformers and the like. So perhaps I'll do more videos about that in the future. But anyway, I wanted to see how a decoder for a binary format could be written using RLMeta. So in this video, I will show you how a QOI decoder can be implemented in RLMeta. Let's jump in. Okay, so I have a folder here for QOI, and at the moment it contains just a REME file and a monument.qi file. So this is a reference QOI image that Francis used, so I've copied it from that repo, and we're going to work with that one. So the first thing I want to do is to import RLMeta, and for that I'm going to grab the latest version from my website, from the blog post that I'm working on. So here it is, the RLMeta poster 2, and there should be a zip file here somewhere. This is it. Let's copy that one. Let's download that and unzip it, and let's just move it to RLMeta. We can remove the RLMeta poster, and let's just do git add and say there we go. Let's start to write the QOI file. So let's call it QOI.RLMeta. Let's just write like this to begin with, and then I want to have the decode script. So let's just run this Python RLMeta compile QOI.RLMeta. Let's see what that does. Yeah, so that works, and now I want to set up a loop that calls this decode script whenever we make changes. So I have a small program for that called command server, and let's do decode and monument.qi. Okay, so whenever I make a save here, I'm sure if you could see that, but let's do that, and you can see that it compiles to something different. So that's good. So let's exit if there are any errors. So let's write a rule called decode. And now we are matching on a stream of bytes, or in our case, I think those bytes will be turned into integers in Python. So the things we have to decode is, first of all, we have to decode the start sequence, and the start is defined in the spec to be this magic bytes QOIF. those magic bytes can be represented like this in hex. So this is the Q in ASCII, 6F, 6.9, and 6.6. And now we will run into our first problem. And that is that the current version of RLMeta does not support matching integers or this hexadecimal notation at all. So if we go into RLMeta and we go into the parser, source parser, there should be somewhere where we match numbers. Let's see. Or we can do pipe string. Yeah, okay, so string. Let's the host expression. So this would be a match expression somewhere. Yeah, over here. So match here somewhere. Match sequence. Yeah, this one. Match object any. So, okay, so let's add it here. I think that'll work. So we will match 0x followed by a hex digit followed by any number of hex digits. And that will be transformed to match object and equals to let's convert that to an integer, the x and the x as in base 16. Okay, so let's see if that might work, and then we have to modify our decode script to first go to and call make.py to create a new version of RLMeta. Okay, expected success. Okay, so we should not have. What did I do then? There should not be a comma there. Okay. And now for the second problem. RLMeta does not support integers in match expressions, so we have to fix that first. Okay, so let's ignore that one first. And we're back with the compilation error here. So, okay, so host expression, string, digit, x digit, star, access. Then we'll call integer and int x access. And then we have to define digit somewhere. So let's do digit 0 to 9. Okay. So now we also have to, in the code generator or assembler perhaps. Yeah, so integer in the assembler, just wrapper. Okay. And so now we can go back to the parser and see if we can do this again. 0x hex, more hex, match object eq int x access 16. So now we can use 16 here. Let's see what it says. No, expected parentheses. Oh yeah, forgot the and parentheses. Right, and now it's complaining that int is not defined. So we have to add that to not there in the support library runtime. We have to add it here, and perhaps yeah, I was a bit. Now it should work. Yeah. Okay, so hex is not defined. Let's define that down here as well. So hex is either 0 to 9 or A to F. Okay, so let's see what happened here. So we managed to create a new version of RLMeta. That's good. And then we continued to work on QOI. And okay, so here I used a small f. I didn't add support for that, so yeah. So I think we are good now. So we can see here that we have match 113, match 111, match 105, and that's probably these as integers. So 71, 113, yeah. So we have now compiled successfully this, and we have added support for matching numbers. So let's modify our decode script and try to run this QOI.py. Let's output it to QOI.py. And we'll also need a main function, so we do copy main.py, and of course that one doesn't exist yet, so let's write it. And then we wanna import this. And then we want to do open sys argv1 in read binary mode. Then we want to create an instance of our QOI class and run the decode rule on the contents of the file. Let's print that as well. Okay, so that worked. we can also, instead of calling this, I think we can use a helper called compile chain, which takes a list, and then the class name, decode, oh, let's see, and then fread. Might that work? Okay, so that works. So that will also give us some extra error handling, and what I wanted to test now was to just change this to 7 perhaps. So now this should fail because it shouldn't match the header. So if we run that, we didn't get a failure because we also need to run python QOI.py with the argument passed to decode. Yeah, so now we're getting another error. Yeah, so this generated class depends on grammar, which is in the support library, and I forgot to generate it, so support, we generate that support library. And I probably used compile chain incorrectly. So let's see, compile chain grammars source grammar rule. Okay, I think that's correct. Compile chain. Oh, so this should be a tuple. Right, like that. Okay, so now this is the binary QOI file. Oh. A bit long. Anyway, I don't want to scroll that. So let's change this back to 66 and we're good. So when it fails, it prints the whole stream and the index where the failure was. But in this case, the stream is so large, so just too much to scroll through. Yeah, so let's just do this. And the result of this decode rule is the result of the start rule, which is the result of the last expression, which is 66 hex, which is 102, and that's what we're seeing here. So after start, we have the width, and it's not defined. An integer is reading 1 byte, called byte 1, reading another byte called byte 2, reading another byte called byte 3, and reading another byte calling byte 4. And now we're just returning the 4th byte because that's the last one, but this is actually in big endians, so we need to do some calculations on these. So what we need to do is to add all these bytes together and shift them. So let's do madd, let's call it that, or we can do msum. And then we do left shift, B1, 24. So this one should be shifted up 24 bits. Same for the rest. But then this case 16. And then 8. And then no shifting for the last one. This doesn't work because these msum and mshift are not defined, so let's define them inside it here. So we had m sum lambda args or args sum args, and then we had left shift xy, which is x shifted y. Okay, so that works, and it means the width of the image is 512 pixels. Let's do the same for the height. 512 pixels. I'm not actually sure if that's correct, but we'll see in a moment, I guess. So let's also return from this both the width and the height as a tuple or as a list. So now we're getting the width and the height of this image. Next we have channels. Let's include that in the result as well. Channels is just a byte, I believe. But according to the spec, it can only have 2 valid values. So let's consult the spec. Channels 3 or 4. So let's do 3 or 4. So this particular image has 4 channels. Color space and color space. Same for that one. It can be 0 or 1. So let's do color space 0 or 1. And let's include it in the output as well. Color space. There we go. Then we have a chunk repeated many times as chunks. I'm not sure if we want to include it here just yet, but we should include it in the result as well. So this will fail probably because chunk does not exist, and chunk is actually the meat of this. So a chunk is any number of things. So let's start with the easiest chunk, which is this one. If the first byte looks like this, then the consecutive 3 bytes are RGB values. So I would like to write this like this in RLMeta. So 0B 1 2 3 4 7 0. But this of course doesn't work because RLMeta does not support matching byte patterns like this. First thing we need to do is to modify the parser to let's see, where did we add the integer? Well, that's for the host expression, so hex, where did we add that one? Yeah, okay, so here. So let's add another one for 0B, and then binary. Let's call it bin. And then here I think we need, when I experimented with this before, the easiest was to add a new instruction in the virtual machine. So let's do match binary, and then add a helper to compile binary, compile bin of this string. And the reason for this is that I would also want to write something like XX and then be able to return those just two top or bottom bits. So let's see. So bin is a 0 or a 1 or A to Z. We can use any letter. Okay, so now we don't have compile bin. Let's add that. Compile bin. Let's just add it here. Positions, or let's see, let's just see what we get here. Yeah, so we're getting 1, 2, 3, 4, 5, 6. So what I made a mistake, so I really want to do return this as a list, so X and then XS. Let's see, what do we get here? Yeah, so 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. This is what I wanted to write. 1, 2, 3, 4, 5, 6, 7, 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So let's see here. Match binary should take this, yeah, like that. And now we want to turn this into something that matches on byte. And I think I wrote this one before, so I'm just going to steal that one. So this is what it looks like. Let's see, I called, what did I call this? Pattern. So if we raise value error, we can raise it with pattern and result. We can see that this is the pattern that we had before, and it has created a mask to match this whole thing. It has created the value that should equal. So we apply this mask to the input, and if it equals this value, then there's a match. And then there's also a place for variables, and I will just show you quickly what that looks like. So if we instead would have written like X here, the mask is different because it's not including the last bit here. The value is the same because we had a 0 before the x, and then here is like information how to extract the x from this byte. So in this case, it says this is the mask and this is the shift. And similarly, if we do, let's say we do y there, we can see that for the y, the mask is 12, and we should shift it to the right 2 steps. So that's how that works. Okay. Going back to support, let's just return the result here as well. Yeah, so now we're getting probably an error in the code generator, I guess, because there's no rule for this match. What did we call it? Match binary. Match binary. So we need to add that in the code generator. So somewhere here we have match. Oh, let's do match object. Match binary. This is the specification. And let's do a new match instruction as well, saying match binary. No. Yeah, okay. Position 1, no match. Let's see. Parser, match binary. It should contain the specification. Okay, so here we have opcode. Yeah, okay. So this must be, let's see, this must be wrapped in a value. Okay, better. And now we also need to implement the match binary instruction. Oops. So here we have match. It looks like that. Let's copy that one and do match binary. So this is the let's call this one pattern. Expected binary. This should probably be something better, but expected binary and the function. The function should be foo, and let's just return false. This is taking the value, or rather byte. Let's call it value. Okay, so that kind of worked. I guess I just looked at what I did before and remembered that in order for this to be complete, we need to do this if match lambda x if x ANDed with pattern mask equals pattern value. Then there is a match. Oops, that's a long line. Never mind that for now. And then we want to do some extra things here. We can remove this one. Okay. And let's come back to this one later, because this is for the variables. So this probably succeeds because it reads 0 chunks, or I don't know, 1 chunk. So let's see if the first chunk is actually this one. We can do that by including the chunks as well and see how many we got. Interesting, yeah. So we got 1. The first chunk in the monument.qi file matched this one. And in this case, we have 3 pixels, or 3 pixel values. The red, green, and blue. And so this one is the red, this one is the green, and this one is the blue. And in that case, let's just return RGB. And then 255 for the alpha. Because this decoder will only it will always represent pixels with 4 values, no matter what's decoded. Okay, so we got a pixel here. This is the red, this is the green, this is the blue, and this is the alpha. Next chunk, we can do this one on ones, which also has the alpha value. And that will be very similar. Let's do that one before. So it will be 1 here, and then RGBA. And didn't contain any alpha value. Index, perhaps. So the index looks like this. We have 2 zeros, and then 1, 2, 3, 4, 5, 6, and X is the index. So we didn't get a match here either. So let's leave that one for now and then do the next one, which is the diff, so 0, 1, 0, 1, and then we have DG diff, or the diff red, diff green, diff blue. Red, green, blue. Yeah, like that. And we didn't get that one either. So let's continue until we get a match so we can get faster feedback. The Luma, so 1, 0. One 0, and then this one is the Luma, and then the next one is split into 2. So 1, 2, 3, 4, 1, 2, 3, 4. It wasn't that either. So what's next? We have the run, which is 1, 1, 1, 1, and then this is the run. Yeah, okay, so now it parsed a lot more, and in the result here we're not converting these to pixels yet. So we're just getting the individual bytes here, or the last byte. But I want to do something more before continuing. When we have parsed all chunks, there should be an end marker. And the end marker is 0, 0. Let's see how many zeros. Where do we find it here? End marker, and an 8-byte end marker. The byte stream's end is marked with 7 of these, and then a 1. So let's do so 1, 2, 3, oops, 1, 2, 3, 4, 5, 6, 7, and then a 1 at the end. And we should call it end. And we couldn't parse this. And I think that's because if we were just going by chunks, this 0, 0, this part here, is going to match, or go over the end marker and match everything. So we need to do here to say not end marker and then this. Yeah. So now we have parsed the end marker, and now there should be no matches left. We should have processed the whole stream, so let's see if we have done that. Yeah, so the parse was successful. We have consumed all bytes in the stream, but obviously these aren't pixel values yet. So let's work on that. 0, 0, let's see what that was. 0, 0 is an index. So this means that this pixel is taken from a running index, an array. So in order to support that, we need to define an array. And the pixel values should be 0, 0, 0 to 55, I believe. And we should multiply this one by 65. So let's see the yeah, so this array has 64 positions, and we will use the 65th position to store the current pixel, which is also needed later. And yeah, this is the default pixel, 0, 0, 0 to 55. So now we have defined this one, and let's also define this multiplication function. And mul lambda x comma y x times y. So here I would also just like to return this just to see what it looks like. So this is the equivalent of in Python doing this times and then a number, say 2. I will need commas. And then we get a list with 2 items where this item is repeated 2 times. And it seems to work here. This is our running array of pixels. So let's call that running. Then we evaluate all the chunks and assign it to a variable, and then turn that variable here. And I'll introduce a helper here called process pixel. this input and process pixel is input, and the process pixel looks like this. So it will take the R, G, B, and A, and it will say that, so we need to set running at position 65 RGBA. So this is saying that the last pixel we have seen is this one. And then return RGBA. Let's see if that works. Okay, so we cannot use set item or wait. List assignment index out of range. Yeah. So the index is 64, the last one. Okay, so that works, nice. And I think now we can get back to this 0, 0. So 0, 0 just says that the next pixel should be taken from this index. So the pixel we return here should be get running 64. And there should be no need to process. Oh yeah, there is a need to process this pixel. Yeah, because it might be a different one. Yeah. So process pixel. Get running 64. Okay, let's see if that works. So that will make sure that the last pixel seen is also set for running, which we will need later. Okay, so that seems to work. So this one right here says that the next pixel is the previous pixel with this difference. So it will be something like this. So I will introduce another helper for this one. So this will be process pixel diff, and it will be let's call it RGB and then the previous pixel. So process pixel diff will get an rdiff, a green diff, RG, and a blue diff, and then this pixel. And it is equivalent to doing run process pixel with, let's see, so some rdiff, some green diff, and some blue diff, and then the alpha. These differences are recorded with a bias, so they can have values -2 to 1. So 0 is -2, so we need to subtract 2 from this difference. We need to write something like m sub rd2 And let's, did we have one for sum? Let's go add sum. So let's add that one down here as well. So m sub x minus y. Let's see if that works. Key error R. Yeah, so now we're coming to this. Now we want to use and this is also incorrect. This should not be get running 64, it should be get running x at that index. But we should get the same kind of error. So yeah, now I need to modify the support line number again for this match binary. So if there's a match, we also need to do a few more things. So let's just remind ourselves what this pattern was. So pattern was this mask with variables. So let's do if pattern has variables. That's what we're interested in here, seeing what that looks like. So yeah, in that case, we want to do for key value in pattern values, items, and we want to do VM.scope key. So let's save this value. We do that by wrapping it in a semantic action. And the value for the semantic action should be so the byte is vm.stream vm.pose -1, because we have advanced one position when this match is done. So the byte should be ANDed with the value mask and right shifted by value shift. See if that makes any sense. Not sure if parentheses are needed there, but let's add them. See if that works. Let's do pattern, and then also let's do vm.scope. You can see what that looks like. Okay, so let's leave that for now. So we can see the values instead of semantic action. So we have x is 6. This might be correct, so let's do that and see. So what we did there was that we actually assigned these two variables that we could later use. Okay, sub should just be called msub. And that worked. Nice, or worked. I'm not sure it worked yet, but we're getting something here. Let's do the same for this one, which is, let's call that lumadiff. So it's this one. So we had the green, and then we have two other variables, and the difference should be calculated like this. And yeah, these values are also stored with a bias. So in this case, 0 means -32, and 0 means 8 in this case. So let's do process lumadiff, and yeah, x, y, z, and this one is called the Z is difference in green, and then we have DRDG, DRDG, and DBDG. Oh, what am I doing? Should not modify this one. Pixel diff, pixel luma. Okay, so in that case we should process the pixel and DRDG, DB, DG. Okay, so let's see. The bias of the green was 31, was it? 32. And then the other two are differences, so let's see. RGB, so what are we adding here? Here we're adding the difference in green. Yes. And these ones should look like this. So these all use the same number, but we add the DRDG, and here we add the DB, DG, should be called DB, DG. So this one should be minus minus 8 more, so minus 40 for these. And process pixel, process luma diff. Okay, I'm not entirely sure about this calculation. I just looked at what I did before and did something similar, so let's see if it works. GD. GD, now it's called DG. DRDG. DRDG. Those were hard to spell. Okay, so we're getting pixels out. I'm not sure if they are the correct ones yet. So we have handled all the cases now except this last one. It means repeat the last pixel run number of times. And 0 in this case means 1, because repeating 0 times doesn't make sense. So in this case, we want to return the get running 64, multiply it by sum x1, and Did we call it sum or did we call it msum? Yeah, msum. Let's support this one. And so I think I messed up the types a bit. This chunks. So chunk. Yeah, chunk. It should really return a list of lists and expand it like that. Removing chunk, so this one just returns 1 pixel. Same for this one. Same for this one. This one as well. This one as well. But this one returns a list of pixels. Yeah, so that's good. That should give them better types. Yeah, it might look okay. But I see here that many pixels are just 0, 0, 0, 0, and I think that's because we forgot to do something. This running array is never filled with anything, so when we process a pixel, we also need to set at some index this pixel as well. And that sum index is calculated like this. So first we do a mod. Let's see if I can format this. Set mod. So we do mod, and then we do sum and sum on multiply the R with 3, multiply the green with 5, multiply the B with 7, and the alpha with 11. This is all according to this formula right here. And I don't think we have mod, so let's add that one. Let's do mod x mod. So these are basically just exposing Python methods to the RLMeta semantic actions. Helps to be able to spell. Missing one, required positional argument y. Yeah, so we have to, of course, pass 64 to mod. Okay, so we're getting a bunch of pixel values here. I'm not sure if this is correct or not, but I know one thing we forgot. And these differences, we also need to do an mod on 255. Because because when you apply, the differences are defined to wrap around. So let's see if that makes any difference. I probably messed up something, but let's see if the pixel values look better now. They do. Okay, so how do we know if these are the correct pixel values or not? So let me copy some code I had before. So for this one, I'll use numpy and peel. And here is the code I have. And let's see, let's write this to, so we have this one, the compilation returns the width, the height, and then, what was it? Color space, something more, pixels equals file chain. Let's do that. Let's see. So width, height, channels, color space, pixels, and this is just some peel code to generate the monument.png file. Pixel height. Let's see if that might work. Okay, so I think this error means that it's not evenly divisible by this height. So what we can do here is we can do print the width, print the height, print the width times the height, and print then pixels. To see what we get. So all chunks produce 1 pixel except the run. This one. Process pixel. Okay, so we should have this many pixels, but we did get this many pixels. A lot more. Okay, so I'm not sure if these are correct. Let's take another look at int 24, 16, and 8. Oh, I see a mistake here. This should be B4. And if I remember correctly, the image did not have the same width and height. So now we are getting better digits here, I think. But this is still the same. Or not the same, but it's a huge difference. Okay, so get running 64. Oh, this one probably has to be written like this. Otherwise it will... Yeah, it's this thing right here. Need to be a list of lists when you multiply it to produce this result. And now we're getting exactly the same, and we have a PNG file. Yes? Let's open it and see. Moment of truth. Wow! Okay, so as we can see, the image resembles something like we have a stop sign and maybe some mountains, so we're not far off here. So let's see if we can find what's wrong. My suspicion is that one of the pixel diffs are not working correctly. So this diff, process pixel diff, RD, they're all biased with -2, right? -2. I think that's sub 32. Should be. $256? No. Is that it? Okay, let's see. No. Let's see. 255 should be the correct one. Yeah, so it was correct. My guess is still that it's this Luma, which is incorrect. Oh, what about this one? Should be X here. And it's getting better. Now we can clearly see that this is an image, but still some artifacts. Okay. So my guess is that the Luma is now correct. because otherwise it wouldn't look this good.
I got a new life, he runs for miles, 67 flashback, oh, it's just my style. We're headed down, down, down the road. Just enjoy the show, watch me as I go.
Okay, I'm back after a short break and trying to figure out what was wrong, and I finally figured out that it was these. These should be mod 256 and not mod 255. I was confusing myself here, I think. So anyway, just to show you, now that we run this, da-da-da-da-da-da, we have, ta-da, nice looking decoded QOI image. Okay, so here we have it. We have written a QOI decoder in 55 lines of RLMeta. And isn't this quite nicely expressed like decode? It says parse all this stuff. This is what it looks like, the byte stream. And a chunk is either this or this or this or this. So I think this reads quite nicely and it's quite densely expressed. These semantic actions, the stuff on the right hand side, does not read very well. So for example, this part right here, if operators were supported, we could write something like R plus RD minus 2 mod 256, and I don't know, perhaps a parentheses or yeah, but you get the point. But RLMeta only has support for basic primitives and function calls, so this is a bit more lispy maybe. I have to express everything and precedence and everything with parentheses. So a nicer syntax for semantic actions could improve the readability of this. And similarly, these things, I mean, this whole expression should be possible to write something like this, which reads quite a lot better, I think. One feature of the QOI format is that it's very fast to encode and decode. We can't really say that for our implementation. Let's have a look. So, our implementation takes 34 seconds to decode a single QOI image, a quite small image. So this is definitely not usable in any kind of practical sense. However, RLMeta has never really been about performance that much, at least. It has been about expressiveness. How cleanly can we express something in this pattern matching language? And hopefully we can improve the RLMeta compiler so it produces more efficient code given this exact same representation. So hopefully we can keep optimizations out of the QOI.RLMeta file so that that can cleanly express the format and how to decode it. And we can apply optimizations to the compiler instead, so that the stuff that the user reads doesn't have to be cluttered by optimizations. Anyway, that's the idea. I'm not sure that will be possible, but perhaps that's a topic for another video. If you like this video, please give it a thumbs up, and if you want to see more videos like this, make sure to subscribe to this channel, and I'll see you in 1 week.